Hi, welcome to my channel. In today's video, I'm going to discuss a particle accelerator by the name of Betatron. So the Betatron, as the name suggests, accelerate charged particles like beta particles. What are beta particles? Well, like an electron. So the mechanism using which Betatron accelerates particles such as electron is actually quite interesting. In this video, I'm going to discuss the mechanism, the principle. But first, let's look at the construction of this kind of a Betatron particle accelerator. So here I have drawn two diagrams. This is the side view of the Betatron and this is the top view of the Betatron. So essentially, the Betatron accelerates electrons using a changing magnetic field. So changing magnetic field is obtained by an electromagnet. So here what you see, the top and bottom region constitute some kind of an electromagnet. So you have some kind of a magnetic core which is wrapped around some kind of a coil through which some alternating current is passing through. So when the current increases and decreases, the magnetic flux also changes. So this represents some kind of an electromagnet. And in this region you have this kind of a donut shaped structure. So this donut shaped structure is an enclosure inside which the electron is revolving, it is moving, it is accelerating. So this donut shaped structure in three-dimensional space is in this region between the two poles of an electromagnet. So basically here you see the cross section of the donut shaped structure, okay, and these lines basically represent the magnetic field lines going from one pole to the other. So in the side view it looks like this. From the top view, this is the donut shaped structure in which the electron is injected at one point, the electron gets accelerated and then it's taken out for the purposes of some sort of a nuclear reaction. Now the Betatron is quite interesting in the manner in which it accelerates electrons. It basically accelerates electrons by using a changing magnetic field. So how it uses a changing magnetic field to accelerate a charged particle, to understand it, let's look at the effect of a changing magnetic field. So when I say changing magnetic field, I basically talk about the consequence of some sort of a current passing through the coil wrapped around this kind of a magnetic core. So when the current is alternating in nature, the magnetic flux is also going to be alternating in nature. The magnetic field is going to increase, it's going to decrease, it's going to change its polarity, and it's going to do this over and over again. So what is the effect of the magnetic field? If you understand the effect of the magnetic field, the entire mechanism of Betatron will be very easy for you to understand. Okay, so let's look at the changing magnetic field, what it does to the motion of a particle like electron. It does two things. Okay, there are two things that the changing magnetic field basically does to the motion of an electron. If you understand both these two things, everything is going to be very easy. The first thing that a magnetic field does, okay, before I come to changing magnetic field, let's look at what a magnetic field does to the motion of an electron. So if there is an electron, let's suppose, which is moving in this plane, okay, and this plane is basically perpendicular to the magnetic field lines, okay, so this is the plane, okay, in which the electron is moving and the magnetic field lines are perpendicular to the plane of the motion of the electron, then what is going to be the trajectory of the electron or any charged particle for that matter? So any charged particle which is moving in a plane perpendicular to the magnetic field lines will execute a circular motion. You probably already know that. So this circular motion is a result of Lorentz force. So Lorentz force is because of the magnetic field acting on a charged particle like an electron. So when an electron experiences a magnetic field, it might be non-changing magnetic field, then it executes a circular motion, first of all. Second of all, when we include this changing part, when the magnetic field is no longer constant, it is changing, what happens? So the changing magnetic field basically creates electromagnetic induction. So what is electromagnetic induction? So you must have heard of electromagnetic induction in the case of a transformer. So in transformer, what happens is that the changing current in a primary coil induces another current in a secondary coil. How does that happen? Well, the changing current in a primary coil creates a magnetic flux which is changing, and that effectively induces an EMF in a secondary coil which leads to the case of a current. Here the primary coil is basically the coil around the electromagnet. So if the current in the coil of the electromagnet is changing like an AC voltage, the magnetic flux is also changing in a sinusoidal manner, and when the magnetic flux changes, then that induces an EMF in the electron's motion. So as the electron is moving inside the donor, then you can associate a current with the electron's motion. So if the electron is moving inside the donut in a circular manner, then you can say that there is a current which is flowing inside the donut itself. So if there is a current which is flowing inside the donut itself, then a changing magnetic field will induce an EMF associated with this current. So this current can be thought of as the current in the secondary coil. Okay, in the same way that in a transformer you have secondary coil, so the electron's motion can be thought of as the secondary coil. So the induced EMF because of the magnetic fields will induce an EMF in the motion of the electron itself. So increasing magnetic field will lead to an induced EMF in the secondary coil, which will try to increase the current. What does it mean? Increasing current, what does it mean? It simply means that the charged particle is going to move with greater velocity. That means the charged particle is going to accelerate. Alright, so in a way, a magnetic field leads to the electron moving in a circle, and a changing magnetic field leads to electromagnetic induction, which basically means accelerating the charged particles. So in a sense, this is the principle of a Betatron. It's similar to the principle of a transformer. So the Betatron is based on a principle that a changing current in the electromagnet induces an EMF in a secondary coil, which basically leads to accelerating the charged particles inside this donut. So this is the main mechanism. The magnetic field creates circular motion of the electron, and the changing magnetic field basically leads to acceleration of the charged particles because of an induced EMF. However, this is not everything. We can look at the different parameters associated with it by looking at the equations involved. Alright, so let's first look at the electromagnetic induction that we are talking about. So if the current in the electromagnet is changing, the magnetic flux is also changing with respect to time. That induces an EMF in the electron's motion inside the donut. Yes. So let's suppose that the magnetic flux associated with this coil in the Betatron electromagnet is phi. Alright, so if the magnetic flux of the coil associated with the Betatron is changing with time, then I can say then the time derivative of the magnetic flux is basically equal to the EMF which is induced in the secondary coil. That means the EMF associated with the current that is associated with the motion of the electron inside the donut. This comes from Faraday's law of electromagnetic induction. Okay, so this is the EMF generated in the secondary coil because of a change of magnetic flux associated with the primary coil. Now because of this EMF, there is going to be a work which is done as the electron is moving in this kind of a circle. So as the electron completes one circular rotation, then what is going to be the work done associated with the motion of the electron because of this induced EMF? The work done associated with the motion of the electron because of this induced EMF is nothing but charge of the particle multiplied by the induced EMF. The charge of the particle is nothing but E. So this is the work done associated with the motion of the electron as it completes one revolution. Now we already know that what is work done? We know that work done is nothing but distance traveled by a particle, let's suppose S, multiplied by the force which is basically creating this kind of a motion. Alright, so let's suppose this force that we are talking about is F1, and S is the distance associated with one revolution. So what is the distance associated with one revolution? It is nothing but the circumference of this circular motion. The circumference is nothing but 2 pi r. So r is the radius of this kind of a circular path, and the force, whatever it is, that is responsible for this kind of a work being done. So on one hand, the work done can be written in this manner. On the other hand, the work done can be written in this manner by definition itself. So these two equations are equal. Yes, so I can say that twice pi r1, sorry, twice pi r f1 is equal to what? E upon epsilon. What is this? This is the induced EMF, which is nothing but E d phi upon dt. So from here I can say that the force associated with this electromagnetic induction is basically equal to E upon twice pi r d phi upon dt. Okay, so this is the force associated with the electromagnetic induction. Let me write down this equation here so that you can view it a little bit better. Okay, so let me write down this equation. So this is the force F1 is equal to E upon twice pi r d phi upon dt. Now this is basically the force because of the induced EMF as the electron is moving in a circular manner. So this force is basically acting in a tangential manner, alright. So if the electron is moving in this particular way, this force is acting tangentially to the motion of the electron's velocity, okay. So this is the force because of electromagnetic induction, which is creating what? It is basically going to change the velocity of the charged particle. See, because of a magnetic field, a charged particle goes in a circular motion, but the magnetic field only changes the direction of the charged particle's trajectory. It does not change the magnitude of the velocity. But in this case, you have a changing magnetic field. So the changing magnetic field will create the effect of a increase in velocity also because of electromagnetic induction. Alright, so this is the force associated with that. Now let's come to the second point. So let's rub this. Now in the second point, I said that the very existence of a magnetic field leads to Lorentz force. Okay, so FL is equal to what? QVB. So if the charged particle has a charge of Q, so in this case we can write E, and if velocity vector is perpendicular to the magnetic field vector, which is in this case, because velocity is in a plane perpendicular to the magnetic field lines, so in this case sine 90 degree will come out to be 1, so we can write Lorentz force is this much. Now what is the effect of a Lorentz force? The effect of a Lorentz force is basically to change the direction of motion of the particle, not the changing the magnitude of the velocity. So this force is basically acting in a radial direction with respect to this circle, okay. So if this circle is a trajectory, this force acts in a radial direction, so it only changes the direction of the charged particle's motion, not the magnitude. So if it changes the direction, it means basically it provides the centripetal force associated with the circular motion, yeah. So this Lorentz force basically provides the centripetal force mv square by r associated with the circular motion of the charged particle moving in a plane perpendicular to the magnetic field. So I can write this equation, okay. So this equation leads to, so VV gets cancelled, is equal to EBR. Now this is kind of an interesting equation because it contains lots of variables. Alright, it contains the velocity, it contains the radius, it contains the magnetic field. Now let's look at all these parameters. So listen to me carefully, okay. There are three variables here: the velocity, magnitude of velocity of the charged particle as the electrons is revolving, the magnetic field, and the radius. Okay, now let's discuss three different cases. First case, in different situation, if the magnetic field is constant, okay. If the magnetic field is constant and the velocity increases, what is going to happen? Velocity is directly proportional to radius. So if the magnetic field is constant, if velocity increases, the radius is also going to increase. That means for a constant magnetic field, increasing the velocity means that the radius is going to increase, so the charged particle is going to spiral outwards. Yes? Now let's look at the second situation. If the velocity is constant but the magnetic field is changing, what is going to happen? Magnetic field and radius are inversely proportional. So if the velocity is somehow constant in a different hypothetical situation and magnetic field is increasing, that means the radius is going to decrease. So if the velocity is constant but if the magnetic field is increasing, then the radius is going to slowly decrease. The particle is going to spiral inwards. Okay, but these two cases are not happening here. What is happening here is that because of electromagnetic induction, there is an induced EMF which is increasing the velocity of the charged particle, yes, but because of electromagnetic induction, the magnetic field is also increasing. Yes, it is changing, it is increasing in the first half of this cycle. So velocity is increasing, magnetic field is also increasing. So what we want to do here is that we want to make sure that the electron retains its radius, that the electron does not spiral outwards, the electron does not spiral inwards. So to do that, you want to increase the velocity at the same rate that you increase the magnetic field so that the radius remains constant. This is in a sense the crux of the Betatron. Increasing velocity increases radius, yes. Increasing magnetic field decreases radius, yes. So basically you increase velocity and you increase magnetic field so that the radius remains constant. This is in a sense the crux of the Betatron, that the because of this force, the velocity will increase at the same rate that the magnetic field is increasing, so that the radius remains constant. This is in essence the Betatron condition. Okay, so to understand the change in velocity and the change in magnetic field, let's do a time derivative. So if I do a time derivative, then this is simply going to be d upon dt of mv, which is equal to er d upon dt of b. I said that the radius is constant, so I can take the radius out of the derivative. What is mv? mv is nothing but momentum. Yeah, so this is associated with the magnitude of the momentum, dp upon dt. What is dp upon dt? It is the force. So this is the force associated with the change in velocity. Now I already told you that the change in velocity magnitude is happening due to electromagnetic induction, so it is happening because of this force. Alright, so this is the force which is responsible for creating the change in velocity in the first place. That means if I write this is F2, then F2 has to be equal to F1. Why? Because this is the force responsible for changing the magnitude of the velocity of the particle in the first place. Now this force is acting tangentially to the motion. Why? This force is in the direction of the velocity vector. So this is in a tangential direction, this force is also in the tangential direction. So let's write this force here. So now I come up with these two equations. This is the force responsible for the increase in the velocity of the charged particle due to electromagnetic induction, and this is the Lorentz force law for a constant magnetic field. Okay, at an instant, if the magnetic field is constant, this is how it's going to be. But since the magnetic field is not constant, in that case I can derive this equation from here itself. So this and this equation has to be same. Why? Because the force responsible for increase in velocity is F1. So basically what we end up getting is this F1 must be equal to this F2. So I can say that if I equate both these two sides, E upon 2 pi r d phi upon dt is equal to ER dB upon dt. So EE gets cancelled and you end up getting this equation d phi upon dt is equal to pi r square. But if you take pi r square inside the derivative, then you get twice d by dt of pi r square b. Okay, so now here this equation is actually quite interesting. This equation basically gives us the crux of the condition at which the Betatron is supposed to work. It is supposed to work at the condition that the change in velocity and the change in magnetic field is going to be such that the radius remains constant. So this equation gives us the idea at which the radius will remain constant. What is B here? B is nothing but the magnetic field at the orbit in which the electron is orbiting this donut. And what is phi here? Phi is the magnetic flux associated with the electromagnet of this particular setup. Okay, so what is phi? So if I write this equation in a little bit different manner, phi can be written as in this particular plane of motion, pi r square b average. Okay, so b average represents the magnetic field associated with the flux, which is for the entire plane of motion, but b here represents the magnetic field in the orbit. So if I write phi is equal to area multiplied by the average magnetic field in the plane of motion, then if I substitute it here, then I can basically take out the derivatives and I can come up with b average is equal to twice b. Okay, so what is b average? B average is the magnetic field due to the flux which is in the entire plane of motion, and B is the magnetic field only at the orbit. So if this condition is satisfied, only in that case the radius is going to be constant. So as the velocity keeps on increasing and the magnetic field keeps on increasing, the radius will be constant only if this condition is satisfied. This condition is known as the Betatron condition or the flux condition. So only when the Betatron condition is satisfied, the rate of change of the velocity and the rate of change of magnetic field is going to be such that the radius is going to be constant. And this condition can be maintained not just for non-relativistic speeds, even when the electron reaches very high speeds, near about relativistic speed, the same condition can be maintained. That means as the particle keeps on accelerating, so as the particle keeps on moving in constant radius, and as its velocity keeps on increasing and it reaches near about the speed of light, even in those cases, if this condition is maintained, the electron can be further accelerated. Now in some particle accelerators like cyclotrons, when you reach relativistic speeds, it stops working, but the Betatron can work even in relativistic speeds. So you can increase the velocity of the electron even when it reaches relativistic speeds, as long as you maintain this condition that the average magnetic field due to the flux in the plane of motion is twice the magnetic field in the orbit of the electron's motion itself. Okay, so the Betatron essentially works with this particular condition to accelerate electrons to very high velocities. That means very high energies. Now when electrons reach very high energies, electrons are charged particle, as it goes around in a circular motion, it basically has a tendency to emit electromagnetic radiation. So when electrons are moving at very high velocities and it sort of radiates electromagnetic radiation, then the kind of electromagnetic radiation which is emitted at such high velocities are X-rays. So Betatrons therefore are also a good source of creating X-rays. Okay, so when the electron is moving at very high velocities, it can be used for generating X-rays, or it can be used for the electron to be used in some sort of a nuclear reaction. You take the electron out and use it in a nuclear reaction. One last thing here, that I told you that the magnetic field is changing in this kind of a manner. However, this kind of an increase in velocity is only going to happen when magnetic field is increasing. If the magnetic field is decreasing, then the particle will experience deceleration. That means this entire process of acceleration must happen in the cycle in which magnetic field is increasing. That means when the magnetic field goes from 0 to some high value, the electron is injected, and when the magnetic field reaches the maximum before it, the electron is taken out. So this entire acceleration happens in the first quarter of this particular cycle of oscillating magnetic field. So this is in a sense the working mechanism and the principle with which the particle accelerator known as Betatron works. I have discussed in my previous videos some other particle accelerators also, like Van de Graaff generators, cyclotrons, synchrotrons, linear accelerators. If you're interested in those, you can check out those videos also. This is all for today. Thank you very much.